All right, let's take a look at a collision involving conservation of angular momentum. Let's say we have a 10-gram dart moving horizontally with a speed of 10 meters per second that collides with and sticks to the edge of a stationary wheel with a radius of 20 centimeters and a mass of 3 kilograms. What would be the angular velocity of the wheel after the collision? Now, in order to begin solving this problem, I'll obviously begin by, writing out my given information. But as I do that, I'm also going to complete this momentum table that I've shown on the right-hand side of my screen here. We use these tables when solving problems involving conservation of linear momentum, and they were a useful tool for us to isolate, certain variables that we were solving for. And so I'll begin just by filling out this table with the information that I've been given in the problem statement. All right. Now, in terms of the momentum of the dart before and after the collision, I know that before the collision, right, the dart has an angular momentum, right? These are all going to be angular momentum values now. What we just defined was that the angular momentum of a point mass, if we consider the dart to be a point mass, then the angular momentum of that dart would just be the mass of the dart multiplied by the velocity of the dart multiplied by the distance of the dart from the center. And in this case, that's just going to be the radius of the wheel. And so I'll write that here. That is going to be the angular momentum of the dart before the collision. All right, now after the collision, I could represent the motion of the dart here. Now, after the collision, the dart is stuck to the wheel. And so they are all moving together as one object. And so the dart is undergoing rotational motion, just like the wheel is, essentially about this point here in the center. We can just call that the center of rotation, right? Center of rotation there. Okay, so after the collision, that would just be equal to the moment of inertia of the dart. So the moment of inertia of the dart multiplied by the final angular velocity that both the dart and the wheel are going to have the same. And so there's my omega final. That's what I'm looking for in this problem, right? I'm looking for that omega final term. And so I already see it there. That's a good sign. And the momentum change of the dart here is just going to be equal to this, after collision minus before collision. All right, so I've just subtracted the term from the after box by the term in the before box. Okay. Now, for the wheel, this is a bit more straightforward. Before the collision, does the wheel have any angular momentum? The answer is no, it doesn't, right? The wheel is not rotating initially, and so we don't have to worry about any angular momentum before the collision. But after the collision, the wheel is rotating, and the wheel itself is going to, the angular momentum of the wheel itself would be equal to the moment of inertia of the wheel, its wheel, multiplied by, again, that final angular velocity. They have the same angular velocity of the wheel and the dart because they're moving together. So here, the change in momentum is just going to be the final momentum, right? The moment of inertia of the wheel multiplied by that final angular velocity. Okay, and so if you add up the momentum of the system, remember the system's momentum is the momentum of each object before and after. We just add them up, right? So this would just be mvr, right? Plus 0 is just mvr. And then after the collision, that's going to be equal to the moment of inertia of the dart times the angular velocity of the system multiplied by the angular, or the moment of inertia of the wheel multiplied by the angular velocity of the system. There we go. And then, again, the momentum change here would be these two terms added together. And so I won't, necessarily worry about that one too much, but I'll write it out for the sake of example. All right, and now recall that for problems involving conservation of angular momentum, which is what we have here, right? The dart and the wheel are our system. There is no net external torque. The wheel is being acted on by the dart when they collide, right? The dart applies a torque to the wheel when they collide, but the dart is part of our system. So that's not an external torque. What that means is the momentum of the system before the collision, right? L system I must equal the momentum of the system after the collision. And so I can just set the momentum of the system before equal to the momentum of the system after. In other words, the momentum of the system, mvr initial, must be equal to the angular momentum, right, angular momentums here, of the system after the collision. So there is our energy conservation equation. You could have gotten the same equation by just setting this momentum change here to 0. right? The momentum change of the system must equal 0. And so if you do that, you would rearrange and you'd get the same exact expression that we have here. Now, I'm solving for the final angular velocity, so I'm going to factor out the final angular velocity from both terms on the right side because I want to isolate that variable. That'll look like this. All right, now I'm going to go ahead and divide both sides of the equation by the sum of those moment of inertias. And if you recall from when we talked about this, what we see here is that the moment of inertia of the system is just the moment of inertia of the dart plus the moment of inertia of the wheel. So we're adding those two terms together. And that's how we treat objects that are traveling like one object. Just we add the moment of inertias together. So that's exactly what we were expecting. That means that the angular velocity of the system after the collision is equal to. All right, and so in this problem, I've been given the mass of the dart, m, lowercase m. I know the velocity of the dart, v. I know the radius of the wheel, r. And I have enough information to solve for the moment of inertias of the dart and the wheel. So just to recap that part, the moment of inertia of the dart is going to be equal to, we're treating this like a point mass, right? We're going to just assume that the dart doesn't really have a shape. It's just a point of mass. So that's just going to be m times d squared, where d is just the distance from the center. So once again, that's just going to be r, the radius, because it is hitting the wheel at the edge. So that would just be equal to mr squared here in this problem, right, in this example. Okay, so we could plug in the mass of the dart. That's going to be in kilograms here. Make sure you convert to kilograms. 0.010 kilograms. That'll give us 10 grams, essentially. Multiplied by that 20 centimeters, so 0.2 meters squared. Okay, in the moment of inertia of the wheel, if you recall, the moment of inertia for a disk is going to be equal to 1/2 m times r squared. So that'd be 1/2. The mass of the disk here is 3 kilograms, and the radius of the disk is the same as the distance the dart hits it, that 0.2 meters. So I'll plug those values in for the moment of inertias that I use in this expression for the final angular velocity. And when I calculate everything, I'll get a final angular velocity of 0.33 radians per second. All right, and so this has been an example of solving a problem involving the conservation of angular momentum. Please make sure that you can do this calculation on your own. I recommend plugging all these values into your calculator as well to make sure that you are plugging in the correct values. Please pay attention to the masses that I used, how we filled out the table. This is a general process that you can apply to any problem involving a collision where there is conservation of angular momentum. I also wanted to say, just for a moment here, in this problem, we can't assume that linear momentum is conserved. And the reason is because if you imagine this wheel is attached to the wall, per se, and the dart hits the wheel, the dart has linear momentum. And so when it hits the wheel, it would also try to impart some of that linear momentum to the wheel. But because the wheel is held by some sort of anchor or some sort of nail or screw to the wall, right, that anchor or that nail or screw is going to push back on the wheel and keep it from moving linearly. And so there is a net external force on this system. It's the force that the anchor point is going to provide on the wheel. And so linear momentum is not conserved. Because we have a net external force, linear momentum is not conserved. However, angular momentum is conserved because there is no net external torque, right? The anchor point is at the center of rotation. It is the center of rotation. And so the lever arm there is 0. Any force that applies on the wheel is not going to produce a torque. And so we can't use conservation of linear momentum, but we can use conservation of angular momentum, treating the dart like a point mass and measuring its angular momentum relative to a point at the center of the wheel. All right, this concludes our series of videos on angular momentum. Please take a look at some practice problems on Canvas to practice your skills.